Every second, a sphere of light expands outward from the place where you rest, now racing at 300,000 kilometers into the darkness, and nothing, no message, no memory, no trace of this moment will ever travel faster than that silent, spreading edge. There is a shape to existence that most never consider. A boundary drawn not by walls or distance, but by the unyielding geometry of space-time itself, curving around each of us like a cocoon we cannot see and cannot leave. The light cone, physicists call it, though it feels more like a gentle enclosure, a quiet certainty that some things will forever remain beyond reach, not because they are hidden, but because the universe simply moves too slowly to carry us there. If these slower passages through strange ideas bring a kind of stillness, perhaps consider staying for more. And so we begin here, with you at the center of something vast. In the year 1676, in the grand halls of the Royal Observatory in Paris, a young Danish astronomer named Ole Rømer sat carefully recording the movements of Jupiter and its moons, as he had done many evenings before, and as he would continue to do for months thereafter, noting with patient precision the exact moments when the small moon called Io disappeared behind the giant planet and then emerged again from its shadow. These eclipses, occurring with what should have been perfect regularity, like the ticking of some celestial clock suspended in the distant reaches of our solar system. And yet, as the weeks and months accumulated into a substantial collection of observations, Rømer began to notice something peculiar, something that did not quite fit the expected pattern, something that would eventually lead him to a conclusion so profound that it would reshape our understanding of the universe itself, though at the time it must have seemed like nothing more than a troublesome discrepancy in his careful records. What Rømer observed, with the quiet attention that characterizes the best scientific work, was that the eclipses of Io did not arrive precisely when his calculations predicted they should. And the nature of this disagreement followed a curious pattern that depended not upon the motion of Jupiter or its moon, but rather upon the position of Earth in its own orbit around the Sun, such that when Earth was moving away from Jupiter on the far side of its yearly journey, the eclipses seemed to arrive later than expected. And when Earth drew closer to Jupiter, approaching from the opposite side of its orbit, the eclipses appeared to arrive somewhat earlier, as if the celestial clockwork were somehow speeding up and slowing down in rhythm with our own planet's wanderings through space, which seemed at first glance to make very little sense, since the motion of Io around Jupiter should have nothing whatsoever to do with where Earth happened to be at any given moment. The discrepancy that Rømer measured amounted to approximately 22 minutes over the course of half a year, which is to say that when Earth was at its most distant point from Jupiter compared to its closest approach, the eclipses of Io arrived about 22 minutes later than one would expect if the information about these eclipses reached us instantaneously. And it was this observation, this careful accumulation of small timing differences, that led Rømer to propose something rather extraordinary for his era, namely that light itself does not travel instantaneously from one place to another, but rather moves at a finite speed, taking measurable time to cross the vast distances between planets, and that the 22-minute delay he had observed represented the additional time required for light to traverse the extra distance across Earth's orbit when our planet was at its farthest point from Jupiter. From this reasoning, working with the best available estimates of the distances involved, Rømer calculated that light must travel at approximately 220,000 kilometers per second, a speed so enormous that it defied easy comprehension, far exceeding anything that humans had ever measured or experienced directly, and yet a speed that was nonetheless finite, limited, and measurable, meaning that the universe was not, as many had assumed, a place where events could be known everywhere simultaneously, but rather a place where information took time to propagate from one location to another, even when that information traveled on the swiftest possible carrier, which appeared to be light itself. And this was a discovery that would eventually prove to be of the most fundamental importance, though its full implications would not become clear for more than 2 centuries. Rømer's estimate of 220,000 kilometers per second was remarkably close to the value we measure today with our far more precise instruments, which is 299,792.458 kilometers per second. A number that has been determined with such extraordinary accuracy that it now forms the basis for our definition of the meter itself. And the fact that Rømer, working in the 17th century with nothing but a telescope and his own patient observations, came within roughly 25% of this value, represents one of the great achievements of early modern science. A triumph of careful reasoning and attention to detail that deserves to be remembered with admiration and gratitude. Nearly 2 centuries after Rømer's observations in Paris, a Scottish physicist named James Clerk Maxwell was working quietly at King's College in London, developing a mathematical framework that would unify 2 seemingly separate phenomena, electricity and magnetism, into a single coherent theory. And in 1865, he published a set of equations that described how electric and magnetic fields interact with one another, how they can create waves that propagate through space, and what the speed of those waves must necessarily be. And when Maxwell calculated this speed from the fundamental constants of electricity and magnetism, which had been measured independently in laboratories, he found that it matched almost exactly the known speed of light, a coincidence that seemed far too precise to be accidental, leading Maxwell to the profound conclusion that light itself must be an electromagnetic wave, a ripple in the combined electric and magnetic fields that permeates all of space. Maxwell's equations predicted that these electromagnetic waves would always travel at the same speed, regardless of how they were produced or observed, and this prediction would later prove to be of immense significance, though at the time it raised a puzzling question that occupied physicists for decades, namely the question of what medium these waves were traveling through, since all known waves, from sound waves in air to ripples on water, required some physical substance to carry them from place to place. And it seemed natural to assume that light waves must similarly require a medium, which scientists called the luminiferous ether, an invisible substance that was thought to fill all of space and through which light propagated like sound through air. In 1887, in the basement of the Western Reserve University in Cleveland, Ohio, 2 American scientists named Albert Michelson and Edward Morley constructed an extraordinarily sensitive instrument called an interferometer, designed to detect the motion of the Earth through this hypothetical luminiferous ether, reasoning that if the Earth were moving through the ether as it orbited the Sun, then light traveling in the direction of Earth's motion should appear to move at a slightly different speed than light traveling perpendicular to that motion. Just as a swimmer moving through a river finds it harder to swim upstream than across the current. And this difference in speed, though expected to be very small, should be detectable by comparing beams of light traveling in different directions and looking for interference patterns that would reveal the tiny timing differences. The Michelson-Morley experiment was a masterpiece of precision engineering, using multiple mirrors to bounce light beams back and forth, increasing the path length and thus the sensitivity of the measurement. And the entire apparatus was mounted on a massive stone slab floating in a pool of mercury to isolate it from vibrations and allow it to be rotated smoothly to different orientations. And yet, when Michelson and Morley carefully analyzed their results, rotating their interferometer and taking measurements at different times of day and different seasons of the year, they found something entirely unexpected, which was essentially nothing. No detectable difference in the speed of light, regardless of the direction in which it traveled. No evidence whatsoever for the motion of Earth through any luminiferous ether. This null result, as it came to be called, was one of the most important negative findings in the history of science, because it suggested that either the ether did not exist, or that there was something fundamentally wrong with the assumptions underlying the experiment, and various physicists proposed various explanations over the following years, including the idea that the ether was somehow dragged along with the Earth, or that objects moving through the ether contracted slightly in the direction of motion, but none of these explanations were fully satisfactory, and the puzzle of the Michelson-Morley experiment remained unresolved for nearly 2 decades. A troubling gap in the otherwise triumphant edifice of classical physics. Albert Michelson continued his work on precision optics and the measurement of light for many years, and in 1907 he was awarded the Nobel Prize in Physics, becoming the first American scientist to receive a Nobel Prize in any of the sciences, an honor that recognized not only his role in the famous ether experiment, but also his many other contributions to the precise measurement of light. And it is worth pausing here to appreciate the quiet persistence of scientists like Michelson, who devoted their careers to ever more careful measurements, ever more precise determinations of fundamental quantities. Work that may seem unglamorous, but which forms the essential foundation upon which all of our deeper understanding is built. What would eventually resolve the puzzle of the Michelson-Morley experiment was a radical reconceptualization of space and time itself, proposed by Albert Einstein in 1905. But we need not rush to that conclusion, for the important point to absorb gently here, as one might absorb the warmth of a blanket on a cool evening, is that by the end of the 19th century, physicists had established beyond any reasonable doubt that light travels at a finite and constant speed, a speed that does not depend on the motion of the observer or the source, a speed that seems to be built into the very fabric of the universe as a fundamental constant, as unchangeable and reliable as any quantity we have ever measured. This constancy of the speed of light would eventually be understood not merely as an interesting fact about electromagnetic waves, but as a deep principle that governs the structure of space and time themselves, placing limits on what can influence what, on what events can be causes and what events can be effects, on the very meaning of the words now and here and there. But for the moment, let us simply rest with the observational facts. with the patient work of Romer and Maxwell and Michelson and Morley, and with the recognition that light, whatever else it may be, is not infinitely fast. Consider what this finite speed means in our everyday experience. Though we rarely pause to notice it, for the light that allows you to see your own hand takes only a tiny fraction of a nanosecond to travel from your skin to your eyes. A delay so brief that it is utterly imperceptible to human consciousness, and yet it is a real delay nonetheless, meaning that you never see your hand as it is at this very instant, but always as it was a moment ago, a moment so short that the distinction seems absurd and pedantic, and yet the principle remains. The light must travel, and travel takes time. When we turn our attention to the wider universe, these delays become more substantial and more significant. For the light from the Sun, our nearest star, requires approximately 8 minutes and 20 seconds to reach the Earth, traversing the 93 million miles between us at that constant speed that Romer first measured and Maxwell first predicted. And this means that when we look at the Sun, whether directly, which one should never do, or filtered through clouds or atmospheric haze, we are not seeing the Sun as it exists at this moment, but rather the Sun as it existed 8 minutes and 20 seconds ago, the Sun of the recent past. And if the Sun were somehow to vanish entirely from existence at this very instant, we would have no way of knowing for another 8 minutes and 20 seconds. We would continue to feel its warmth and see its light as if nothing had happened, living in blissful ignorance of a catastrophe that had already occurred. This is not a metaphor or a philosophical thought experiment, but a straightforward physical fact. And it applies not only to the Sun, but to everything we see, from the nearest objects to the most distant galaxies. Each of them revealed to us, not as they are now, but as they were when the light we are receiving left them on its journey toward our eyes. And the farther away something is, the further into its past we are looking, which gives astronomy its peculiar character as a science that studies not only distant places, but also ancient times. Each telescope, a kind of time machine that shows us the universe as it once was. The Moon, being much closer than the Sun, sends us light that is only about 1¼ seconds old. And so when we gaze at the Moon on a clear night, we are seeing it almost as it is, just a heartbeat behind the present moment. But the nearest star beyond our Sun, a small red dwarf called Proxima Centauri, is so far away that its light takes more than 4 years to reach us, meaning that the Proxima Centauri we see in our telescopes is not the Proxima Centauri of today, but the Proxima Centauri of more than 4 years ago. And anything that has happened there since then, any changes in its brightness or activity, are still unknown to us. The news traveling toward us, even now, at that constant and unhurried pace. And so we come to understand that light, which seems so instantaneous in our daily lives, which fills a room the moment we flip a switch and reveals the world to us without any perceptible delay, is in fact a messenger that moves at a finite speed, the fastest messenger there is, according to everything we have learned, but finite nonetheless. And this finiteness is not a minor technical detail, but a fundamental feature of the universe we inhabit, one that will have profound implications for our understanding of causality, of time, of what it means for events to happen simultaneously, and ultimately of the invisible boundaries that surround each of us. boundaries defined by this constant speed that we cannot exceed and cannot escape. In the early months of 1905, in the quiet Swiss capital of Bern, a young man of 26 years made his way each morning along the cobbled streets toward a modest office building on Speichergasse. The building housed the Federal Office for Intellectual Property, which is to say, the Patent Office, and the young man's title was that of technical expert. Third class. His name was Albert Einstein, and his duties consisted primarily of examining patent applications for various electrical devices, assessing their novelty and their feasibility, writing careful reports in the measured language of bureaucratic precision. The work was not especially demanding for someone of his abilities, and this, as it turned out, was rather fortunate, for it left him with time to think. And thinking, for Albert Einstein, was something very close to breathing. The office itself was unremarkable in every way that offices tend to be unremarkable. There were desks arranged in rows, windows that admitted the grey light of Swiss winters and the softer gold of Swiss summers, inkwells and blotters and stacks of paper describing inventions of varying degrees of practicality. Einstein's desk was positioned among others belonging to his colleagues, civil servants who processed the steady stream of applications with professional diligence. The sounds of the office were the sounds of any office of that era, the scratching of pen nibs, the shuffling of documents, the occasional murmur of consultation between one expert and another. And yet, within this thoroughly ordinary setting, behind the mild expression of a young man with unruly dark hair and a rather informal manner of dress, something extraordinary was taking shape. Einstein had been thinking about light for a very long time. The thoughts had begun when he was 16 years old, a student at the cantonal school in Aarau, a small town not far from Zurich. In those days, he had struggled with the rigid discipline of his previous school in Munich, and the more relaxed atmosphere of the Swiss institution suited him better, allowed his mind to wander along paths that formal instruction often discouraged. And wander it did, persistently, toward a particular question that refused to leave him in peace. He imagined himself chasing after a beam of light, running alongside it, faster and faster, until perhaps he might catch up with it entirely. What would he see? He wondered. If he could travel at the same speed as light itself, what would a light wave look like if one were moving alongside it, keeping pace with its crests and troughs? This was not a question that could be answered by any experiment then available. It was purely a matter of imagination, of following the logic of known physics to see where it might lead. And where it led was troubling. According to the physics of the time, the physics built upon the magnificent edifice of James Clerk Maxwell's equations describing electricity and magnetism, a light wave should appear frozen if one could travel alongside it at light's own speed. The oscillating electric and magnetic fields that constitute light should appear stationary, a static pattern hanging motionless in space. But Maxwell's equations contained no provision for such a stationary solution. A frozen light wave was not something those equations could describe. There was a contradiction here, a quiet inconsistency buried in the foundations of physics, and the young Einstein could not stop thinking about it. 10 years passed. Einstein completed his studies at the Swiss Federal Polytechnic in Zurich, an institution known more formally as the Eidgenössische Technische Hochschule, or ETH. He struggled to find an academic position, applied for jobs that did not materialize, worked briefly as a tutor and a substitute teacher. He became a Swiss citizen, married a former classmate named Mileva Maric, and eventually secured the position at the patent office through the assistance of a friend's father. His academic ambitions had not vanished, but they had been set aside, placed in a drawer labeled later, while he earned his living examining other people's inventions. Yet, through all of this, the question of light remained with him, turning slowly in his mind like a stone being polished by a stream. In the spring of 1905, something shifted. The pieces that had been accumulating for years, the paradoxes and the partial insights and the stubborn contradictions, began to arrange themselves into a coherent picture. Einstein later recalled a conversation with his friend Michel Besso, a fellow patent office employee and a patient sounding board for physical ideas, that helped him finally see the path forward. The key, he realized, lay in reconsidering something that everyone had always taken for granted, something so fundamental that it seemed beyond question. He had to reconsider the nature of time itself. By June of that year, Einstein had completed a paper of approximately 9,000 words, written in German with the unhurried precision of someone who has thought very carefully about what he wishes to say. The title was On the Electrodynamics of Moving Bodies, a rather modest heading for a work that would eventually reshape humanity's understanding of the universe. He sent the manuscript to Annalen der Physik, one of the leading physics journals of the German-speaking world, where it would be reviewed and, in September, published. The paper contained no references to other literature, no footnotes acknowledging previous work, only a brief thank you to Michel Besso in the final paragraph. It was as if Einstein had arrived at these ideas entirely through the force of his own contemplation, which, in large measure, he had. The argument of the paper rested upon two postulates, two starting assumptions from which everything else would follow. The first postulate stated that the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply a perspective from which objects not acted upon by forces appear to move in straight lines at constant speeds, or to remain at rest. If you are sitting in a train carriage that glides perfectly smoothly along a straight track at unchanging velocity, and you drop a ball, it falls straight down to the floor exactly as it would if the train were standing still in the station. You cannot tell, from any experiment conducted inside that sealed carriage, whether you are moving or stationary. The laws of physics, Einstein proposed, do not distinguish between these situations. Motion at constant velocity is entirely relative, and no inertial frame is more correct or more fundamental than any other. The second postulate was more startling, though Einstein stated it with characteristic simplicity. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. This was the crucial insight, the lever that would move the world. Imagine a lamp mounted on the front of a train moving toward you at great speed. Common sense might suggest that the light from that lamp should reach you faster than light from a stationary lamp, just as a ball thrown from a moving train travels faster relative to the ground than a ball thrown from a stationary position. But light, Einstein declared, does not behave this way. Whether the lamp approaches you or recedes from you, whether you yourself are moving toward it or away from it, the light it emits travels toward you at exactly the same speed, approximately 299,792 kilometers per second. Never faster, never slower, always precisely the same. At first glance, this seems impossible. If the speed of light is constant regardless of how the source or the observer moves, then something else must give way to accommodate this constancy. And indeed, something does give way. What Einstein showed, with careful mathematical reasoning, was that our intuitive notions of space and time are the things that must bend. If light speed is to remain the same for all observers, then observers in relative motion must disagree about other quantities that had previously seemed absolute. They must disagree about the lengths of objects. They must disagree about the durations of intervals. They must even disagree about which events happen at the same time. This is not a matter of perception or measurement error. It is not that one observer is correct and the other mistaken. Both are equally correct from their own perspectives. The disagreement is built into the structure of reality itself. Time, which had always seemed to flow uniformly for everyone, like a great river carrying all events along at the same pace, turned out to be something more personal, more dependent upon one's state of motion. A clock moving relative to you ticks more slowly than a clock at rest beside you. A measuring rod moving past you is shorter, in the direction of its motion, than an identical rod at rest. These effects are tiny at everyday speeds, far too small to notice, but they grow more pronounced as speeds increase, and they become dramatic as one approaches the speed of light. The paper made its way into the world quietly, read by specialists, discussed in the small community of theoretical physicists who paid attention to such things. It was not met with immediate acclaim or universal acceptance. Some found it convincing, others puzzling. Still, others simply ignored it. Einstein himself returned to his desk at the patent office, continued examining applications, continued thinking about physics. That same year, 1905, he published 3 other papers of extraordinary significance, including one explaining the photoelectric effect that would eventually earn him a Nobel Prize, and another establishing the theoretical basis for understanding Brownian motion. It was a remarkable year, later called his miracle year, though at the time Einstein remained an obscure patent clerk, unknown to the wider public, waiting to see whether his ideas would find acceptance. Understanding came gradually, and one of the most important contributions to that understanding came from an unexpected source. Hermann Minkowski was a mathematician who had taught at the ETH Zurich during Einstein's student years. He had, in fact, been one of Einstein's professors, lecturing on mathematics to a young man who, by his own later admission, did not attend classes as faithfully as he might have done. Minkowski had apparently considered the young Einstein rather lazy, an impression that the student's sporadic attendance and informal manner would have done little to dispel. But whatever his earlier opinion, Minkowski recognized the importance of what Einstein had achieved, and he saw something in the equations of special relativity that Einstein himself had not fully appreciated. In 1908, Minkowski delivered a lecture to the Assembly of German Natural Scientists and Physicians in Cologne. The lecture was titled Space and Time, and it began with a declaration that would echo through the century to come. Henceforth, Minkowski announced, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This was not poetic exaggeration, but a precise mathematical statement. Minkowski had realized that Einstein's relativity could be understood most clearly not as a theory about space and time separately, but as a theory about a single unified entity, a four-dimensional continuum that Minkowski called space-time. In this picture, the universe is not a three-dimensional stage upon which events unfold as time passes. Instead, it is a four-dimensional structure in which all events simply exist, located at particular positions specified by 3 spatial coordinates and 1 temporal coordinate. What we experience as the passage of time is, in some sense, our movement through this structure, tracing out a path called a world line. Every object, every particle, every person has a world line, a thread woven through the fabric of space-time, marking where and when that object exists. The mathematics of this description is elegant and revealing. In ordinary three-dimensional space, the distance between 2 points can be calculated using the Pythagorean theorem, adding together the squares of the differences in each coordinate and taking the square root. Minkowski showed that a similar formula applies in space-time, but with a crucial difference. The temporal coordinate enters the calculation with an opposite sign from the spatial coordinates, a subtraction rather than an addition. This small algebraic change has profound consequences. It means that space-time is not simply four-dimensional space of the ordinary kind. It has a different geometry, a geometry in which some intervals are positive, some negative, and some precisely zero. The intervals that are precisely zero are particularly significant. They correspond to paths through space-time that could be traced by a beam of light. Light, traveling at its constant speed, marks out a boundary in space-time, a surface separating what is accessible from what is not. And this brings us to something that Minkowski's geometric perspective made suddenly and strikingly clear. The fusion of space and time into space-time did not merely simplify the mathematics of relativity. It revealed something that no one had anticipated, a structure inherent in the geometry, a boundary surrounding every event that determines what can influence it and what it can influence. This boundary is not a wall that you can touch or a line that you can see. It exists in the abstract geometry of space-time itself, a consequence of the constant speed of light and the peculiar arithmetic of Minkowski's interval formula. It is inescapable, not because it is enforced by any force or barrier, but because it is woven into the very definition of distance and duration, into the fabric from which the universe is made. Every event in space-time is surrounded by this boundary, and nothing, no signal, no influence, no information of any kind, can cross it in the forbidden direction. Einstein, when he first learned of Minkowski's geometric reformulation, was not immediately enthusiastic. He reportedly described it as superfluous learnedness. an unnecessary mathematical complication of ideas that he felt he had expressed more directly. But in time, he came to appreciate the power of the space-time perspective, and when he later extended his theory to include gravity, producing the general theory of relativity, Minkowski's geometry proved indispensable. The shadows that space and time had become, in Minkowski's poetic phrase, turned out to be the very substance from which Einstein would construct his greatest achievement. And so, from a thought experiment imagined by a 16-year-old schoolboy in Aarau, through a decade of patient contemplation, to a paper sent from a patent office in Bern, to a lecture in Cologne that fused space and time into a single whole, a new understanding of the universe emerged. It was quieter than most revolutions, conducted in equations and lectures and the pages of scholarly journals, but its consequences were as far-reaching as any upheaval in human thought. Among those consequences was the discovery of a boundary, an invisible prison that surrounds each of us, that has always surrounded us, that will surround us for as long as we exist within this universe. The next portion of our exploration will examine the nature of this boundary more closely. But for now, we may simply rest with the knowledge that it exists, that it was always there, waiting to be discovered, a quiet feature of the geometry of space-time that governs what is possible and what is not. Let us now turn our attention to the shape itself, the geometry of this invisible boundary that travels with you always. And to do so, we shall need to speak of diagrams, of the elegant visual language that physicists developed in the early 20th century to make sense of what had become a rather bewildering new understanding of space and time. The tools we shall examine were not created to confuse or to impress, but rather to clarify, to take the mathematics of relativity and render it visible upon a page, so that one might see at a glance what equations alone can sometimes obscure. And in this spirit of gentle illumination, we shall proceed. The diagrams in question are called spacetime diagrams, or more specifically, Minkowski diagrams, named for Hermann Minkowski, the German mathematician who had once been Einstein's teacher in Zurich and who, in 1908, presented a geometrical interpretation of special relativity that would forever change how physicists visualize the universe. Minkowski stood before an assembly of scientists in Cologne and declared that henceforth space by itself and time by itself were doomed to fade away into mere shadows, and that only a kind of union of the two would preserve an independent reality. This was not poetry, though it sounds rather like it, but rather a precise mathematical statement about the structure of the cosmos, and the diagrams that bear his name are the visual expression of this profound union. Imagine, if you will, a piece of paper, though we must ask this paper to do rather more work than paper ordinarily does, for it must represent not merely the spatial dimensions we are accustomed to, but also the dimension of time. We draw upon this paper two axes, as one does in ordinary geometry, but here the vertical axis represents time, flowing upward from past to future, while the horizontal axis represents space, or at least one dimension of space, for we cannot easily draw all three spatial dimensions alongside time without venturing into territories that paper cannot follow. This simplification, reducing space to a single line while keeping time as another line, allows us to see the essential features of space-time without becoming lost in dimensional complexity. And it is in this spirit of useful simplification that physicists have worked with such diagrams for more than a century. At the center of this diagram, where the two axes cross, we place a point, and this point represents here and now. This particular location in space at this particular moment in time. And it is from this point that we shall draw the light cone. The light cone emerges from this central point in a distinctive shape, formed by drawing diagonal lines that extend both upward and downward, representing the paths that light rays would take if they were emitted from or absorbed at this central event. Because we have agreed to measure things in units where the speed of light becomes a natural standard, these diagonal lines are drawn at 45 degrees to the vertical, slanting away from the time axis at an angle that represents the maximum possible speed of any causal influence. The upward-pointing portion of this shape, expanding as it rises into the future, is called the future light cone, and it encompasses all those events in spacetime that could possibly be reached by a signal originating at the central point, all those places and times that lie within causal reach of here and now. The downward-pointing portion, narrowing as it descends into the past, is called the past light cone, and it contains all those events from which a signal could have arrived at the central point, all those places and times whose influence could possibly have touched here and now. The two cones meet at their tips, at the single point of the present moment, and together they form a shape rather like two ice cream cones joined at their narrow ends. Or perhaps two hourglasses placed tip to tip, expanding infinitely in both temporal directions. It is worth pausing to consider why this shape is called a cone rather than some other geometrical form. For on the flat page of a diagram with only one spatial dimension, it appears more like two triangles meeting at a point, or perhaps a sideways hourglass. The terminology becomes clearer when we remember that we have suppressed two of the three spatial dimensions for the sake of drawing, and that if we were to restore even one more spatial dimension, adding depth to the page, the diagonal lines would sweep out into curved surfaces, and the triangular shapes would become true cones trains, circular in cross-section and expanding smoothly in all directions. Add the third spatial dimension, though we cannot truly draw this, and the cones become four-dimensional hypercones. But the essential geometry remains the same. And so the name light cone persists even in our simplified two-dimensional drawings. To make these abstractions more tangible, let us consider an event occurring far from Earth, something dramatic and luminous that might send light traveling across the vast distances between the stars. In the direction of the constellation Andromeda, there exists a galaxy, our nearest large galactic neighbor, situated approximately 2.537 million light-years from where you are resting now. If a supernova were to explode in that distant galaxy, a massive star ending its existence in a catastrophic detonation of light and matter, the photons from that explosion would begin their journey toward Earth at the speed of light, which is, after all, the only speed at which photons ever travel. These photons would cross the intergalactic void, traversing the emptiness between galaxies, passing through the sparse hydrogen that drifts in those immense spaces, and eventually After 2.537 million years of traveling, they would arrive at Earth and enter our instruments, our telescopes, our eyes. What this means, when we think of it in terms of light cones, is that the explosion itself, the event of the supernova detonating in Andromeda, would not enter our past light cone until those 2.537 million years had elapsed. Before that moment of arrival, the supernova would exist in a region of space-time entirely disconnected from our experience, neither in our past nor accessible to our future, simply elsewhere in the geometry of the cosmos. And then, at the precise moment when the light reaches us, the event would cross into our past light cone, becoming part of the history that can affect us, becoming knowable and real in the only sense that physics allows us to speak of distant events being real. There is a star rather closer to home that provides an even more striking illustration of these principles. A red supergiant in the constellation Orion known as Betelgeuse, which marks the hunter's shoulder in the patterns our ancestors drew upon the night sky. Betelgeuse is approximately 700 light-years distant from Earth, which is practically next door in cosmic terms, but still an almost incomprehensible distance by any human measure. Astronomers have long known that Betelgeuse is in the late stages of stellar evolution, and that it will eventually explode as a supernova, producing a burst of light so bright that it will be visible in daylight. A new star appearing where Orion's shoulder once glowed red. When that light reaches us, when astronomers around the world turn their instruments toward the sudden brilliance in Orion and announce that Betelgeuse has exploded, we must remember that the explosion itself will have occurred 700 years before our observation. That the star we watched explode will have actually ended its existence during what we call the medieval period on Earth, during the centuries when cathedrals were being built in Europe and the Mongol Empire was expanding across Asia. This is not merely a curiosity or a trick of perspective, but a fundamental feature of the universe's geometry. The Betelgeuse that we see tonight, should you gaze upon Orion before sleep, is Betelgeuse as it existed 7 centuries ago, and we have no possible way of knowing what is happening there now, at this present moment, because the light from that present moment has not yet arrived, and by the deep structure of space-time, it cannot arrive any faster than it is already traveling. The now of Betelgeuse and the now of Earth are separated in a way that prevents any communication, any influence, any knowledge from passing between them until the light has made its journey. The British physicist and cosmologist Hermann Bondi, who spent much of his career at Cambridge and London, developed particularly beautiful ways of explaining these concepts to students during his lectures in the 1960s. Bondi had a gift for taking the mathematical formalism of relativity and translating it into vivid images and clear explanations, and his 1965 lectures at Cambridge became legendary among students of physics for their clarity and elegance. He would draw the light cones carefully upon the blackboard, explaining how they divided space-time into distinct regions, how the boundaries of the cones represented the absolute limit of causal connection, and how events outside the cones were not merely far away, but fundamentally unreachable, separated from us by the geometry of the universe itself. Bondi understood that these ideas, which can seem abstract and remote when expressed in equations, become more accessible when one can see them, when the shapes themselves tell the story. And it is through considering these shapes that we encounter one of the most profound features of relativistic space-time, the region that physicists call elsewhere, or sometimes the absolute elsewhere. This is the portion of space-time that lies outside both the future light cone and the past light cone, the vast region that contains most of the universe at any given moment. All those events that are neither in our accessible future nor in our influential past. Events in the elsewhere region cannot affect us and cannot be affected by us. Not because they are too far away in any ordinary sense, and not because we lack the technology to reach them, but because the very geometry of space-time forbids any causal connection between them and us. This is a strange and somewhat unsettling concept when first encountered. This idea that most of what is happening in the universe right now is absolutely disconnected from us. That there exist vast regions of space where events are unfolding at this very moment that can never influence our lives, and that we can never influence in return. But as one grows accustomed to thinking in these terms, there is something peaceful about it as well. Something restful in the recognition that we are not responsible for those distant events, that they proceed according to their own physics without any possibility of our intervention, and that the universe is far larger than any single light cone can encompass. The technical term for what light cones define is causal structure, and this phrase captures something essential about what relativity has taught us. The causal structure of space-time is the pattern of what can possibly affect what, the geometry of influence and connection that underlies all physical processes. When we say that event A can cause event B, we are making a statement about causal structure. We are saying that B lies within the future light cone of A, that there exists a path through space-time along which influence can travel from A to B without exceeding the speed of light. And when we say that two events are causally disconnected, that neither can affect the other, we are saying that each lies in the elsewhere region of the other, outside both light cones, unreachable by any physical process. Every point in space-time has its own light cone, its own future and past, its own accessible regions and its own elsewhere. And this means that every particle in the universe, every atom, every electron, carries with it a light cone centered on its current position, a personal boundary of causal possibility. You carry a light cone with you as you rest, listening to these words. And so does every atom in your body, and so does every object in your room, and so does every star in the sky. The light cones overlap and intersect in complicated ways, but each is centered on its own particular here and now. Each defines its own particular division of the universe into reachable and unreachable. Consider yourself and a friend standing together, side by side, in the same room. Your light cones are very nearly identical, almost indistinguishable, because you are separated by perhaps a meter of space, and your clocks, such as they are, read very nearly the same time. But technically, mathematically, your light cones are distinct, centered on slightly different points in space-time, and there are events, absurdly remote events admittedly, that lie just within one light cone and just outside the other. The difference is vanishingly small, imperceptible in any practical sense, but it is there, written into the geometry of the universe, a reminder that each observer, each point of view, each here and now, is ultimately unique, and so The light cone is not merely a diagram on a page, not merely a teaching tool or a mathematical convenience, but a representation of something fundamental about the universe we inhabit, about the invisible boundaries that surround each moment and each location, defining forever what can be known and what must remain unknown, what can be reached and what must remain beyond our grasp. And so we come now to the moment when the barrier, as we might call it, begins to reveal itself, not through dramatic collision or sudden halt, but through something far more subtle and, in its own quiet way, far more absolute. This is the story of what happens when you try to cross the boundary of your own light cone. And it is a story told not in speculation, but in careful measurement, in laboratories and aircraft and mountaintops, where patient scientists have watched the universe gently but firmly redirect every attempt to breach this invisible geometry. Let us begin in the year 1964, in a basement laboratory at the Massachusetts Institute of Technology, where a physicist named William Bertozzi was conducting an experiment that would make visible something Einstein had predicted decades earlier. Bertozzi was working with electrons, those impossibly small particles that orbit atomic nuclei and carry electrical charge, and he had designed an apparatus to accelerate them to extraordinary speeds. The machine he used was a linear accelerator, a long tube through which electrons could be pushed by electromagnetic fields, gaining energy with each passing moment. And Bertozzi's intention was straightforward in conception, though demanding in execution. He wished to measure, with great precision, both the velocity of the electrons and the energy required to achieve that velocity, and in doing so, to trace the curve that connects speed to the effort needed to attain it. What Bertozzi found, and what he published for others to examine and confirm, was that this curve behaved in a most peculiar manner as the electrons approached the speed of light. At lower velocities, the relationship was roughly what one might expect from ordinary experience, where doubling the energy produces a noticeable increase in speed. But as the electrons crept closer to light speed, something strange began to happen. The additional energy poured into the system produced smaller and smaller gains in velocity. The electrons reached 99% of light speed, and then 99.9%, and then 99.98%. And at each step, the energy required for the next tiny fraction grew not merely large, but disproportionately, almost unreasonably large. Bertozzi's measurements showed that to push those electrons from 99.98% to 100% of light speed would require not merely more energy, but an infinite amount of energy, more than exists in all the stars of all the galaxies in the observable universe combined. This is what physicists sometimes call relativistic mass increase, though the terminology has evolved over the decades and modern treatments prefer to speak of relativistic momentum. But the essential observation remains unchanged. As an object with mass approaches the speed of light, it behaves as though it is becoming harder and harder to accelerate, as though its resistance to further pushing grows without bound, and this resistance becomes infinite, precisely at the boundary we have been discussing. Bertozzi's electrons could approach that boundary as closely as the energy available would permit, but they could never reach it, and certainly never cross it. The barrier revealed itself not as a wall to crash against, but as a horizon that recedes exactly as fast as you approach. Always present, always the same distance away in some fundamental sense, no matter how much effort you expend. 7 years later, in 1971, two scientists named Joseph Hafele and Richard Keating conducted an experiment of a rather different character, one that would reveal another face of this same barrier. Their apparatus was, in a sense, far simpler than Bertozzi's accelerator, consisting of 4 cesium beam atomic clocks, the most accurate timekeeping devices then available to science, though their accuracy would seem quaint by modern standards. These clocks measured time by counting the oscillations of cesium atoms, which vibrate at a frequency so stable and so precisely known that the second itself is now defined in terms of these oscillations. Hafele and Keating placed their clocks aboard commercial Pan Am aircraft, those great jetliners that once connected the cities of the world, and flew them around the entire planet, first in an eastward direction and then on a separate journey westward. The purpose of this aerial circumnavigation was to test Einstein's prediction that time itself passes at different rates depending on relative motion. According to the theory of special relativity, a clock that moves relative to you will tick more slowly than your own clock, and this slowing becomes more pronounced as the relative velocity increases. The effect at everyday speeds is vanishingly small, far too tiny to detect with ordinary watches or even with most scientific instruments. But cesium atomic clocks are sensitive enough to measure differences of billionths of a second, and Hafele and Keating hoped to catch time dilation in the act, as it were. When the aircraft returned and the traveling clocks were compared to reference clocks that had remained stationary on the ground, the results matched Einstein's predictions with remarkable precision. The eastward flying clocks, which had been moving faster relative to the Earth's center due to the combination of the aircraft's speed and the planet's rotation, showed less elapsed time than the ground clocks by approximately 59 nanoseconds, while the westward flying clocks, which had been moving slower relative to the Earth's center, showed more elapsed time by approximately 273 nanoseconds. These numbers accorded exactly with what relativistic calculations foretold, and the experiment was repeated and refined in subsequent years with consistent results. What Hafele and Keating had demonstrated was that the barrier surrounding your light cone affects not merely how fast you can travel, but how time itself flows for you as you travel. The closer you approach light speed, the more slowly your clocks tick relative to those you leave behind. And at light speed itself, if you could reach it, time would stop entirely for you while continuing to flow for everyone else. This is not a metaphor or a manner of speaking, but a literal physical fact, verified by experiment and incorporated into the design of technologies we use every day. But we need not rely solely on human-built machines to observe these effects, for nature herself conducts experiments on a vast scale, and one of the most elegant of these involves particles called muons. Muons are created when cosmic rays, those high-energy particles that rain down upon our planet from distant stellar explosions and other violent cosmic events, collide with atoms in the upper atmosphere. These collisions produce showers of secondary particles, among them muons, which are somewhat like electrons but considerably heavier and, crucially for our purposes, quite short-lived. A muon at rest will decay into other particles in approximately 2.2 microseconds, which is to say about 2 millionths of a second, and even traveling at nearly the speed of light. A muon should only be able to cover about 600 meters before it transforms and ceases to exist. Yet muons created in the upper atmosphere, some 10 or 15 kilometers above the Earth's surface, routinely reach sea level in great numbers, arriving at our mountain tops and our beaches and our instruments as though the journey presented no difficulty whatsoever. This observation puzzled physicists in the early 20th century until relativity provided the explanation. The muons are traveling so fast, at velocities exceeding 99% of light speed, that time dilation stretches their brief existence from our perspective. Their internal clocks run slowly, their decay processes are correspondingly delayed, and what seems to them like 2 microseconds of existence appears to us as dozens of microseconds, time enough to traverse the entire atmosphere and reach the ground. This phenomenon was observed and measured with particular care in 1941 by Bruno Rossi and David Hall, who set up detectors on Mount Washington in New Hampshire and at sea level below, counting the muons that arrived at each location and comparing the results. The ratio they found matched exactly what relativity predicted once time dilation was taken into account, and could not be explained by any other mechanism. The muons themselves, if they could report their experience, would insist that they lived only their customary 2 microseconds. But they would also report, quite correctly, that the distance they needed to travel had contracted, shrunk from 15 kilometers to perhaps 600 meters due to another relativistic effect we shall discuss in a moment. Both descriptions are equally valid. Both are equally true, and together they paint a consistent picture of a universe where time and space are woven together in ways that reveal themselves only at extreme velocities. This brings us to length contraction, traction, the sibling of time dilation, which describes how distances themselves appear shortened in the direction of motion for objects traveling at relativistic speeds. An observer watching a spaceship fly past at 90% of light speed would measure that spaceship to be considerably shorter than its occupants, would measure it to be compressed along its direction of travel as though squeezed by invisible hands. And the occupants of that spaceship, looking out at the universe rushing by, would see all external distances similarly contracted, the stars and planets pressed closer together along their path. Neither perspective is wrong, neither is an illusion, and both are required to make sense of what experiments reveal. We must pause here to mention a technology that depends upon these corrections every moment of every day. One that most people carry in their pockets without ever considering the relativistic computations humming away invisibly overhead. The Global Positioning System, which tells us our location on Earth's surface with remarkable accuracy, relies upon signals sent from a constellation of satellites orbiting approximately 20,000 kilometers above us. These satellites carry atomic clocks of extraordinary precision, and they broadcast timing signals that receivers on the ground use to calculate distances and triangulate positions. The system was developed through the efforts of many scientists and engineers, among them Roger L. Easton Sr., whose foundational work in satellite navigation earned him recognition as one of the principal architects of GPS. For this system to work correctly, the clocks aboard the satellites must remain synchronized with clocks on the ground to within a few nanoseconds. And this is where relativity becomes not merely interesting, but essential. The satellites are moving relative to the Earth's surface at approximately 14,000 kilometers per hour, which causes their clocks to tick more slowly due to time dilation by about 7 microseconds per day. But they are also higher in Earth's gravitational field, where gravity is weaker, and this causes their clocks to tick faster due to an effect from general relativity by about 45 microseconds per day. The net result is that satellite clocks run faster than ground clocks by approximately 38 microseconds every day. And if this were not corrected, positioning errors would accumulate at a rate of about 10 kilometers per day, rendering the system useless within hours. The engineers who designed GPS understood this, and they built relativistic corrections into the satellite clocks from the very beginning, adjusting their tick rate before launch so that they would synchronize properly with ground-based time once in orbit. Every time you check your phone's map application or follow navigation instructions to an unfamiliar destination, you are relying upon Einstein's theory of relativity to guide you, and upon the careful measurements of scientists like Bertozzi and Hafele and Keating and Rossi and Hall, who demonstrated that these effects are not mathematical curiosities, but physical facts that shape our daily lives. And here, perhaps, we arrive at the deepest truth revealed by all these experiments and observations, which is that the boundary of your light cone is not enforced by any wall or barrier in the conventional sense. There is no surface you could touch, no membrane you could press against, no sign reading that you shall not pass this point. The enforcement mechanism is far more fundamental and far more gentle and far more absolute. It is the geometry of reality itself, the shape of space-time curving away from you in every direction, arranged in such a way that the paths you might take through existence simply do not include any that cross into regions beyond your cone. The mathematics describing this is quite beautiful in its own austere fashion, involving intervals that can be positive or negative or zero, depending on whether they connect points within your reach or beyond it. And these intervals remain unchanged, no matter how fast you travel or how much energy you expend. And so, we come now to consider the largest prison of all. One so vast that the word prison seems almost absurd, and yet one so absolute that it makes the constraints we have discussed thus far seem almost trivial by comparison, for there exists around you, around the earth, around the sun and all the stars you have ever seen, a boundary that is growing ever more confining with each passing moment. Not because anything is physically closing in, but because the universe itself is stretching, carrying distant regions away from us faster than light could ever hope to traverse the growing gulf between here and there. This cosmic event horizon, as it is called, represents the ultimate boundary of your light cone, the furthest edge beyond which no information, no signal, no traveler could ever reach us, not because of any physical barrier in the conventional sense, but because the very fabric of space is expanding at such a rate that certain regions are receding from us faster than the speed of light. And while this might seem to violate everything we have discussed about nothing exceeding light speed, it does not. For it is not that objects are moving through space faster than light, but rather that space itself is stretching, carrying those distant galaxies away as if they were dots painted on an inflating balloon, each dot remaining stationary on the balloon's surface, while nonetheless growing further from every other dot as the balloon expands. The discovery of this accelerating expansion is remarkably recent in the history of science, having been firmly established only in 1998, which means that for most of human history, and indeed for most of the history of modern physics, we did not know that the universe was conspiring to make itself ever more inaccessible to us, ever more sealed off from observation, ever more confined within shrinking horizons. And the story of this discovery is itself rather gentle and methodical, involving patient observations of distant stellar explosions and careful measurements of how their light had been stretched during its long journey to our telescopes. The two teams that independently arrived at this startling conclusion were the Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory in California, and the High Z Supernova Search Team, led by Brian Schmidt, who is himself Australian, as it happens, working alongside Adam Rees and numerous other collaborators scattered across institutions around the world. And both teams were engaged in what they expected would be a relatively straightforward, if technically demanding, measurement of how quickly the universe's expansion was slowing down. For it was generally assumed at the time that the gravitational attraction of all the matter in the universe would be gradually applying the brakes to the expansion that began with the Big Bang, much as a ball thrown upward slows as it rises against Earth's gravity. To make this measurement, both teams turned to a particular type of stellar explosion known as a Type Ia supernova, which occurs when a white dwarf star, the dense remnant of a sun-like star that has exhausted its nuclear fuel, accumulates material from a companion star until it reaches a critical mass of approximately 1.4 times the mass of our Sun, at which point it undergoes a thermonuclear detonation of such consistency and predictability that these explosions serve as what astronomers call standard candles, objects of known intrinsic brightness that can be used to measure cosmic distances. For if you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it must be, just as you might estimate the distance to a lighthouse if you knew the wattage of its lamp. One particularly well-documented example that contributed to this research was supernova 1994D, observed in the outskirts of a galaxy designated NGC 45266, located in the constellation Virgo, and this explosion, along with dozens of others observed over several years, provided the data points that both teams used to construct a history of cosmic expansion, measuring how fast the universe was expanding at various epochs in the past by observing supernovae at various distances, and thus at various look-back times. Since the light from a supernova 1 billion light-years away shows us what was happening 1 billion years ago, and the light from a supernova 5 billion light-years away shows us conditions 5 billion years in the past. What both teams found, to their considerable surprise, was that the distant supernovae were fainter than they should have been if the universe's expansion were slowing down, and fainter even than they would be if the expansion were proceeding at a constant rate. And the only explanation that fit the data was that the expansion of the universe was accelerating, speeding up over time rather than slowing down, as if some mysterious repulsive force were pushing the cosmos apart with ever-increasing vigor. And this discovery was so unexpected, so contrary to prevailing assumptions, that both teams checked and rechecked their results with considerable care before announcing them. And when they did publish their findings, the scientific community was initially skeptical, though subsequent observations from multiple independent sources have since confirmed the accelerating expansion beyond reasonable doubt. And in 2011, Perlmutter, Schmidt, and Rios shared the Nobel Prize in Physics for their discovery. The force responsible for this acceleration has been given the rather placeholder name of dark energy, which is an acknowledgement of our ignorance rather than a genuine explanation, for we do not know what dark energy is, only that it behaves as if space itself possesses some intrinsic property that causes it to expand at an accelerating rate. And the more space there is, the more of this expansive tendency there is, leading to a runaway acceleration that will, over billions of years, make the visible universe an increasingly lonely place. The immediate consequence of this accelerating expansion for our cosmic prison is the existence of what is called the cosmic event horizon, which represents the boundary beyond which light emitted today will never reach us, no matter how long we wait. And this boundary is currently located at a distance of approximately 16 billion light-years, which means that any galaxy currently beyond that distance is receding from us so rapidly that photons it emits right now, at this very moment, as you lie there listening to these words, will never, ever reach Earth. Not in a million years, not in a billion years, not in the entire future history of the universe, for those photons are swimming against a current that is stronger than they are, making headway in their local region of space, while nonetheless being carried backward overall by the expansion of the intervening regions, like a fish swimming upstream in a river that is flowing faster than the fish can swim, so that despite its earnest efforts, the fish moves ever further from its destination. And this leads us to a subtle but important distinction between what is called the observable universe and the universe as a whole. For the observable universe is defined as that region from which light has had time to reach us since the Big Bang, and it has a diameter of approximately 93 billion light-years, which might seem peculiar given that the universe is only about 13.8 billion years old and light can only travel at light speed. But the explanation lies again in the expansion of space. For light that began its journey toward us from the very early universe has been traveling all this time, while space has been stretching behind it, so that the objects that emitted that light are now much farther away than they were when the light set out. And the 93 billion light-year figure represents the current distance to those objects whose ancient light is only now reaching our telescopes. But this observable universe, vast as it is, containing some 2 trillion galaxies by recent estimates, is almost certainly smaller than the whole universe, which may be enormously larger, perhaps infinitely larger, though we cannot know for certain, since we can only observe what lies within our particle horizon, which is another way of describing the boundary of the observable universe, the surface beyond which no light has yet had time to reach us. And while this horizon has been expanding since the Big Bang as ever more ancient light finally arrives, The accelerating expansion means that the cosmic event horizon is now shrinking in terms of what regions will ever become accessible to us, creating a situation in which we are gaining access to some new regions while permanently losing access to others. These nested horizons, the particle horizon representing what we can see now, and the event horizon representing what we will ever be able to see, create a kind of cosmic prison within a prison, boundaries within boundaries, each defining a different limit on our access to information about the universe. And yet, it must be said that even the inner prison, the observable universe within which we find ourselves, is so incomprehensibly vast that the word prison seems almost comically inadequate. For we are speaking of a volume containing more galaxies than there are grains of sand on all the beaches of Earth, each galaxy containing hundreds of billions of stars, many of those stars circled by planets, the whole ensemble representing a richness of potential experience and exploration so far beyond any individual human's capacity to exhaust that the constraints, while absolute, are in no practical sense confining. It is worth pausing here to acknowledge that the idea of an expanding universe itself has a history, and that history involves one of the more gracious acknowledgements of error in the annals of physics. For the Belgian physicist and Catholic priest Georges Lemaitre first proposed in 1927 that the universe was expanding, basing his conclusion on Einstein's equations of general relativity and on early observations of distant galaxies. And when Lemaitre presented his ideas to Einstein, the great physicist is reported to have dismissed them as abominable physics. So contrary were they to Einstein's own conviction that the universe must be static and unchanging on the largest scales, a conviction so strong that Einstein had added an artificial term to his equations, the so-called cosmological constant, specifically to prevent them from predicting an expanding universe. And it was only later, after Edwin Hubble's observations had confirmed that distant galaxies were indeed receding from us, that Einstein acknowledged his error and reportedly called the cosmological constant his greatest blunder. Though, in a curious twist, that same cosmological constant has been revived in modern physics as a possible explanation for dark energy, so perhaps it was not such a blunder after all. The observational evidence for the accelerating expansion and the existence of cosmic horizons has been greatly aided by the Hubble Space Telescope, that patient instrument orbiting above Earth's atmosphere, gathering light from the most distant reaches of the cosmos. And among its many contributions has been the documentation of galaxies so distant that their light has been stretched by the expansion of space to such a degree that they are barely visible even to the most sensitive instruments. Their light redshifted to longer and longer wavelengths. And this redshift is a direct measure of how much space has expanded since the light began its journey, with the most distant observed galaxies showing redshifts so extreme that they are seen as they were when the universe was less than 1 billion years old, when the first stars and galaxies were just beginning to form. And as the expansion continues to accelerate, these distant galaxies will redshift further and further, their light stretching to longer wavelengths, their images growing fainter and fainter, until eventually they will redshift beyond the capacity of any instrument to detect, fading into invisibility as if they had never existed. Though, of course, they still do exist, somewhere out there beyond our ability to perceive, their stars burning, their planets orbiting, their civilizations, if any exist, going about their business entirely unaware of us, just as we will eventually become entirely unaware of them. And this fading into invisibility is not some distant concern of the far future, for it is happening now, continuously, as the expansion carries more and more of the universe beyond our event horizon. And while no individual galaxy will visibly wink out in a human lifetime, the process is nonetheless relentless. What we are left with, then, is the somewhat sobering but also oddly comforting realization that we exist within a series of nested light cones and cosmic horizons, each defining a limit on what we can observe, what we can interact with, what we can ever hope to reach or be reached by. And while these limits are absolute in the physical sense, they are also so extraordinarily generous, encompassing such an incomprehensible vastness of space and time and possibility, that to call them a prison is perhaps to miss the point entirely. For a prison that contains trillions of galaxies and spans billions of light years and offers more complexity than any mind could ever comprehend, is a prison only in the most abstract philosophical sense, and in every practical sense it is simply home. The only home we have ever known or will ever know, and knowing its boundaries. Understanding why those boundaries exist and what they mean is itself a kind of freedom, the freedom that comes from knowledge, from understanding, from the patient accumulation of facts about the universe in which we find ourselves embedded. And so we come now to consider what might be called the boundaries of our visible world, the very edges of everything we can observe or measure or know through any instrument yet devised by careful human hands. And we find there something rather beautiful waiting for us, something patient and ancient and full of information, if only we learn how to receive it properly, with the right sort of attention and the right sort of equipment, and perhaps most importantly, with the right sort of quiet willingness to listen. You will recall that we have spoken of the light cone as a kind of prison, though prison is perhaps too harsh a word for something so fundamental and so impartial. And we have described how nothing within this universe can travel faster than light through the vacuum of space, which means that there exists for each of us, and indeed for every point in space-time, a region beyond which no information can reach us no matter how long we wait, a region that remains forever causally disconnected from our present moment, as inaccessible as a dream that someone else is having in a room we cannot enter. But the edges of this prison, if we may continue to use that word for the sake of continuity, are not blank walls of featureless nothing, not empty barriers of pure absence, but rather something far more interesting and far more generous. For the universe has provided us with a kind of wallpaper at the limits of our observable region, a faint and ancient glow that fills every direction we might choose to look. And this glow carries within it information about the earliest times we can ever hope to observe directly, the earliest light that could ever reach us from those distant epochs when the cosmos was young and hot and very different from the cool and scattered arrangement of galaxies we see today. This ancient light has a name, and it is called the cosmic microwave background, or sometimes simply the CMB for convenience, and it represents what we might think of as the wall of our observable universe. Not a physical wall made of any material substance, but a wall of time, a surface beyond which ordinary light cannot carry any message because the universe itself was opaque before that moment, filled with a fog of charged particles that scattered photons endlessly and prevented them from traveling any appreciable distance without being absorbed and re-emitted in random directions. The light of the cosmic microwave background was released approximately 380,000 years after the Big Bang, which may sound like a very long time, but is actually quite brief in cosmic terms. Barely a heartbeat compared to the nearly 14 billion years that have elapsed since then. And it was released during an epoch that cosmologists refer to as recombination, when the universe had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms for the first time. And this transition from charged particles to neutral atoms meant that suddenly, quite suddenly, on cosmic timescales, the universe became transparent to light. And all those photons that had been bouncing endlessly through the hot plasma were suddenly free to travel in straight lines across the cosmos. And they have been traveling ever since, stretched and cooled by the expansion of space itself, their wavelengths elongating from the hot glow of visible light to the much cooler and longer wavelengths of microwaves. The discovery of this ancient light is a story worth telling, slowly, for it involves the kind of accidental scientific progress that seems almost too perfectly ironic to be true. And yet, it happened exactly as the records indicate, at a place called Bell Telephone Laboratories in Holmdel, New Jersey, where two radio astronomers named Arno Penzias and Robert Wilson were working with a rather unusual instrument in the year 1965. The instrument in question was called the Holmdel Horn Antenna, and it had been built originally for satellite communication experiments. A large horn-shaped receiver designed to detect very faint radio signals bounced off balloon satellites in orbit. And when those experiments concluded, Penzias and Wilson decided to use the sensitive equipment for radio astronomy to study the faint emissions from our own galaxy. And this required them to account for every possible source of noise in their instrument, every stray signal that might interfere with the delicate measurements they hoped to make. What they found, much to their frustration, was a persistent hiss of microwave radiation that seemed to come from everywhere in the sky, not from any particular direction, not from any identifiable source, but uniformly from all directions at once. And this noise corresponded to a temperature of approximately 3 degrees above absolute zero, a faint warmth pervading all of space. And try as they might, they could not eliminate it or explain it through any instrumental effect they could imagine. They checked their equipment repeatedly. They rebuilt components. They examined every possible source of interference. And they even discovered that pigeons had been nesting inside the horn of the antenna, leaving behind what the scientific literature delicately refers to as a white dielectric material, which is a polite way of saying that the birds had left their droppings inside this precision instrument. And Penzias and Wilson carefully cleaned out this material and removed the pigeons, which sadly had to be dealt with rather permanently to prevent their return. And yet, even after all this effort, the mysterious hiss remained exactly as it had been before, coming from every direction, constant and inexplicable. The explanation, when it came, arrived through a fortunate chain of communication between scientists at different institutions. For it happened that a group of physicists at nearby Princeton University, led by Robert Dicke and including a young theorist named Jim Peebles, had been working on predictions about what the early universe might have been like. And they had calculated that if the Big Bang theory were correct, there should be a faint afterglow of radiation filling all of space, cooled by billions of years of cosmic expansion to a temperature of just a few degrees above absolute zero. And they were actually in the process of building their own antenna to search for this radiation when they learned that Penzias and Wilson had already found it, quite by accident, while trying to eliminate what they had assumed was merely unwanted noise. The accidental nature of this discovery does not diminish its importance, for what Penzias and Wilson had detected was nothing less than the oldest light in the universe, the first electromagnetic radiation that could travel freely through space, and it carried within it information about the state of the cosmos when it was only a few 100,000 years old, a baby photograph of the universe itself. And for this discovery, they would eventually receive the Nobel Prize in Physics in 1978. But the cosmic microwave background, as Penzias and Wilson observed it, appeared almost perfectly uniform, the same temperature in every direction to remarkable precision. And while this uniformity was itself significant, it also presented a puzzle. For if the early universe were perfectly smooth and homogeneous, it would be difficult to explain how the lumpy distribution of galaxies and clusters we see today could have arisen. And so, cosmologists began to search for tiny variations in the temperature of the CMB, fluctuations that would indicate slight differences in the density of matter in the early universe, seeds from which all the structure we observe would eventually grow through the patient action of gravity over billions of years. These fluctuations were eventually found by a satellite called COBE, which stands for Cosmic Background Explorer, launched by NASA in 1989 and carrying instruments designed specifically to map the cosmic microwave background with unprecedented precision. And in 1992, the COBE team announced that they had detected tiny ripples in the temperature of the ancient light, variations so small that they amounted to only about 30 millionths of a degree, plus or minus 300 thousandths of a degree from the average temperature, which is to say, differences of approximately 0, Alka, EOA, N003 degrees Kelvin from one part of the sky to another. These minuscule variations, invisible to any instrument before COBE, were the imprints of quantum fluctuations from the earliest moments of cosmic inflation, stretched to cosmic scales and frozen into the distribution of matter when the universe was still incredibly hot and dense. And they would eventually grow under the influence of gravity to become all the galaxies and clusters and vast cosmic structures we observe today. Every star and planet and living creature ultimately traceable back to these faint wrinkles in the temperature of the ancient light. The lead scientist of the COBE team was an American physicist named George Smoot, and when announcing the discovery, he remarked that observing these fluctuations was like seeing the face of God, by which he meant something poetic rather than theological, an expression of awe at glimpsing the very structures from which everything we know would eventually emerge, the primordial pattern from which all complexity would unfold. And while some found this language too dramatic and others found it not dramatic enough, the sentiment beneath it remains understandable. For there is something genuinely moving about detecting signals that have traveled for nearly 14 billion years to reach our instruments, carrying news of a time before any stars existed, before any galaxies had formed, before anything recognizable as structure had emerged from the hot, smooth soup of the early cosmos. The measurements of the CMB have continued to improve in the decades since Kobe, with increasingly sophisticated satellites mapping the ancient light with ever greater precision and resolution. And among the most significant of these more recent missions was the Planck satellite, launched by the European Space Agency in 2009 and named after the German physicist Max Planck, whose work on blackbody radiation laid the theoretical foundations for understanding thermal emissions of exactly this kind. The Planck satellite was positioned at a location called the Second Lagrange Point, or L2, which sits approximately 1.5 million kilometers from Earth in the direction opposite to the Sun, a gravitationally stable position where the satellite could keep the Earth, Moon, and Sun all behind it while observing the cold sky, shielded from the warmth of these nearby bodies. And from this vantage point, it mapped the cosmic microwave background with such exquisite precision that cosmologists could extract detailed information about the composition and geometry and age of the universe, determining among other things that the cosmos is approximately 13.8 billion years old, that it is geometrically flat to within our ability to measure, and that its contents consist of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, though what exactly these latter two components are remains among the deepest unsolved questions in physics. But the cosmic microwave background, for all its importance, represents only one kind of messenger that the universe sends to us: electromagnetic radiation in the form of light or radio waves or microwaves. And in recent years, we have learnt to detect other messengers entirely. Signals that travel through space by means quite different from the oscillations of electric and magnetic fields. And these new messengers open windows onto cosmic events that light alone could never reveal to us. The most dramatic of these new messengers are gravitational waves, ripples in the fabric of space-time itself, predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, but so faint and so difficult to detect that nearly a century would pass before human technology became sensitive enough to observe them directly. Gravitational waves are produced whenever massive objects accelerate through space, but for the waves to be strong enough to detect at astronomical distances, the objects must be extraordinarily massive and must be moving at extraordinary speeds. And the most powerful sources of gravitational waves are cataclysmic events involving the most extreme objects in the universe. Things like neutron stars and black holes, spiraling together and merging in violent collisions that shake the very structure of space and time. The first direct detection of gravitational waves occurred on September 14, 2015, when twin detectors operated by the LIGO collaboration, one located in Livingston, Louisiana, and the other in Hanford, Washington, simultaneously registered a characteristic signal that swept upward in frequency over the course of approximately 0.2 of a second. A chirp of gravitational radiation produced by two black holes spiraling together and merging into a single larger black hole, approximately 1.3 billion light-years from Earth. The signal that reached Earth that September day was almost inconceivably faint, corresponding to a stretching and squeezing of space by an amount smaller than 1/10,000th the diameter of a proton, and detecting it required lasers bouncing back and forth through 4-kilometer-long vacuum tubes. measuring changes in distance with precision that would have seemed like science fiction only decades earlier. And the fact that two detectors, separated by thousands of kilometers, both registered the same signal at nearly the same moment, with a slight delay consistent with the gravitational waves traveling at the speed of light between them, provided confirmation that the detection was genuine and not merely some local disturbance or instrumental artifact. Those two black holes, in their final moments of separate existence, had been orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. And when they merged, they released more energy in that fraction of a second than all the stars in the observable universe were radiating at that moment. But that energy was carried away in the form of gravitational waves rather than light, invisible to every telescope ever built, detectable only by instruments designed specifically to feel the stretching and squeezing of space itself. And there is yet another messenger that the universe sends to us, one that predates even our detection of gravitational waves. And these are the neutrinos, ghostly particles with almost no mass and almost no interaction with ordinary matter. Particles so reluctant to engage with the material world that they can pass through the entire Earth as easily as light passes through a pane of glass. And yet, for all their elusiveness, we have learnt to catch a few of them, now and then, in enormous detectors buried deep underground to shield them from other forms of radiation. In February of 1987, a star exploded in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way at a distance of approximately 160,000 light-years. And this supernova, designated SN 1987A, was the closest stellar explosion observed since the invention of the telescope, bright enough to be visible to the naked eye in the southern hemisphere. And it provided astronomers with an unprecedented opportunity to study the death of a massive star in detail. But before the light of the explosion reached Earth, before any telescope detected the brightening of that distant star, a handful of neutrinos arrived first. Messengers that had escaped from the collapsing core of the dying star hours before the shock wave reached the surface and produced the visible flash. And these neutrinos were detected by the Kamiokande 2 experiment in Japan. A large tank of water buried deep in a mine, surrounded by sensitive light detectors designed to catch the rare flashes produced when a neutrino happens to interact with a water molecule. 25 neutrinos were detected in total, arriving over a span of about 13 seconds, approximately 3 hours before the optical light from the supernova reached Earth. And while 25 may seem like a pitifully small number, it represents a significant fraction of the neutrinos that we had any hope of detecting from such a distance. And it confirmed theoretical predictions about the physics of stellar core collapse, providing direct evidence about conditions at the very heart of a supernova, a region so dense and so violent that light itself is trapped for hours while neutrinos stream freely outward, carrying away most of the energy released in the explosion. The neutrinos arrived before the light, not because they traveled faster, for they too move at or very near the speed of light, but because they could escape from the core of the collapsing star immediately, passing through the dense stellar material as if it were not there, while the light was trapped for hours as the shock wave worked its way outward through the outer layers of the star. And this difference in arrival time taught us something profound about the internal dynamics of supernovae, information that no optical telescope could have provided. And so we see that even within the confines of our light cone, even bounded by the unbreakable speed limit that physics imposes upon all information and all causation, the universe is remarkably generous with its messages, sending us ancient light from the dawn of transparency, sending us gravitational waves from the merger of black holes billions of years ago and billions of light years away, sending us ghostly neutrinos from the hearts of exploding stars, each messenger carrying different information, revealing different aspects of the cosmos, and together painting a picture far richer than any single type of observation could provide. We cannot escape our light cone. This is true. But the universe sends messengers to its edges, and we have learned, with great patience and great ingenuity, to receive them. And so we come now to a rather tender part of our discussion, the part where we must gently close certain doors that the imagination might wish to leave ajar. And in doing so, we will discover something rather unexpected, which is that these closed doors are not barriers to wonder, but are in fact the very foundations upon which wonder can exist at all. And this realization, when it settles upon you, carries with it a particular kind of peace, the peace of understanding that the universe is not withholding something from you out of spite or indifference, but is rather structured in precisely the way it must be structured for you to exist as a being capable of asking these questions in the first place. Let us begin with the wormholes, those passages through space-time that have captured the imagination of so many dreamers and storytellers, and which do in fact emerge quite naturally from the mathematics of general relativity, appearing first in a paper published in 1935 by Albert Einstein and his colleague Nathan Rosen, who were working together at the Institute for Advanced Study in Princeton, New Jersey, where the autumn leaves would have been falling outside their windows as they explored the strange geometries hidden within Einstein's field equations. And what they found was a solution that described a kind of bridge, a tunnel connecting two separate regions of space-time, which we now call an Einstein-Rosen bridge, though at the time Einstein and Rosen were not proposing these as practical pathways for travel, but rather as mathematical curiosities that might help explain the nature of fundamental particles. And the structure they discovered was elegant in its own way. A throat of curved space-time linking what appeared to be two different universes, or perhaps two distant regions of our own universe, folded together like a piece of paper brought to touch itself. For many decades, these bridges remained purely theoretical, interesting solutions to equations, but nothing more. Until, in 1988, a physicist named Kip Thorne, working at the California Institute of Technology, together with his student Michael Morris, published a paper in Physical Review Letters that asked a deceptively simple question, which was whether it might be possible, even in principle, for a wormhole to be traversable, meaning that something or someone might actually pass through it and emerge on the other side. And their analysis, conducted with the careful rigor that characterizes the best theoretical physics, revealed that traversability would require something very particular, something that does not appear to exist in the ordinary matter we encounter in our daily lives. And this requirement is for what physicists call exotic matter, matter that possesses negative energy density, which is to say matter that weighs less than nothing, that gravitates in reverse, pushing rather than pulling. And while quantum field theory does suggest that very small regions of negative energy density might exist in certain carefully constructed situations, the amounts required to hold open a wormhole of any useful size would be so vast, and the conditions so extreme, that the universe appears to have arranged itself in such a way that these bridges, if they exist at all, pinch themselves closed faster than anything could traverse them. And there is something rather soothing about this, when you think about it in the gentle quiet of an evening settling into night. Because the mathematics is not arbitrary. It is not a rule imposed from outside, but rather the natural consequence of how gravity and energy and the fabric of space-time relate to one another. And these relationships are the very same relationships that allow stars to shine and planets to orbit and you to rest upon your bed without falling through it. So the closure of this particular door is not separate from the opening of all the other doors through which ordinary reality pours. We might then turn our attention to another proposed escape route, one that emerged in 1994 from the mind of a Mexican physicist named Miguel Alcubierre, who was at the time a graduate student, and who asked whether it might be possible to move through space faster than light without ever locally exceeding the speed of light. And the answer he found was theoretically yes, by means of what we now call the Alcubierre drive, or sometimes the Alcubierre warp drive warp, which works not by accelerating an object through space, but by contracting the space ahead of the object and expanding the space behind it, so that the object rides inside a bubble of flat spacetime that itself moves faster than light relative to distant observers. Like a surfer riding a wave who never actually moves through the water faster than the wave itself. And this solution was remarkable because it seemed to obey all the local rules of relativity while violating its global spirit. And for a brief moment, it appeared that perhaps the light cone might not be quite so confining after all. But the Alcubierre solution, beautiful as it is mathematically, carries within it requirements that appear to place it beyond any practical realization. For the warping of space-time in the manner required would demand quantities of negative mass energy so stupendously vast that they beggar comprehension, with early calculations suggesting that the energy required would be equivalent to the entire mass of Jupiter converted to energy and then made negative, which is rather a lot. And while subsequent refinements by various physicists over the following decades managed to reduce these requirements somewhat, the fundamental need for exotic matter with negative energy density remained, linking the Alcubierre drive to the same constraint that closes the wormholes, and suggesting that perhaps the universe has woven this particular thread through multiple fabrics, ensuring that the light cone remains inviolable not through a single prohibition, but through a harmony of interlocking physical principles. Now, we must speak of quantum entanglement, because there is perhaps no phenomenon in all of physics that has generated more hope for faster-than-light communication, and more subsequent disappointment when that hope is examined carefully. And the story is worth telling, slowly, because it reveals something profound about the nature of information itself. And it begins with a paper published in 1935, the very same year as the Einstein-Rosen bridge paper, in which Einstein, together with Boris Podolsky and Nathan Rosen, described what they considered to be a troubling feature of quantum mechanics, which was that two particles that had interacted and then separated could remain correlated in their properties in a way that seemed to imply instantaneous influence across arbitrary distances. And Einstein found this deeply unsettling, calling it spooky action at a distance. And for decades, the question of whether these correlations were truly instantaneous or whether they might be explained by some hidden mechanism remained unresolved. The resolution came through the work of a physicist named John Bell, who in 1964 derived a set of inequalities that would be violated if quantum mechanics were correct and upheld if some hidden local mechanism were responsible for the correlations. And then, beautifully, experimentally, in 1982, a French physicist named Alain Aspect, working in Paris with his colleagues, performed a series of exquisitely designed experiments that measured the polarizations of entangled photons and found, with increasing precision over multiple experimental runs, that Bell's inequalities were indeed violated, meaning that quantum mechanics was correct and that the correlations between entangled particles were genuine, non-local, and in some sense instantaneous. And for a moment, this might seem to offer exactly the escape from the light cone that we have been discussing. But here is where the universe reveals its deep elegance, its careful architecture, because, while the correlations are instantaneous, while measuring one particle does immediately affect what we can say about its entangled partner, regardless of the distance between them. This instantaneous correlation cannot be used to send information, and the reason is subtle and beautiful, which is that the outcome of any quantum measurement is fundamentally random, so that when you measure your particle and find a certain result, your distant partner's particle will indeed show a correlated result when they measure theirs, but you had no control over what result you would get, and therefore you have transmitted no message. You have merely created a correlation that can only be discovered by comparing notes, and the comparison of notes must happen through ordinary channels, through light or radio or physical travel, all of which are bound by the light cone. So the entanglement, real and strange and wonderful as it is, offers no escape from the gentle prison of causality. We should speak now of time, because escaping one's light cone is in a very real sense escaping into one's own past, and the universe appears to have thoughts about this as well. Thoughts that were articulated most clearly by Stephen Hawking in 1992 when he proposed what he called the chronology protection conjecture, which states, in essence, that the laws of physics conspire to prevent the creation of closed time-like curves, which is the technical name for paths through space-time that loop back upon themselves, paths that would allow you to travel into your own past. And Hawking observed that whenever physicists attempted to construct such loops, whether through rotating cylinders or carefully arranged wormholes or any other mechanism, the quantum effects associated with the attempt always seemed to grow without bound, generating infinite energies that would destroy the time machine before it could function. And while this remains a conjecture rather than a proven theorem, the consistency with which these obstacles appear suggests that the universe is protecting something, protecting the causal order that we experience so effortlessly that we forget it requires protecting. The danger of closed time-like curves is not merely abstract, for they would allow what are called causal paradoxes, the most famous being the grandfather paradox, in which you travel back in time and prevent your own birth. thereby ensuring that you never exist to travel back in time, thereby ensuring that you do exist, after all. And this logical tangle is not merely a puzzle for philosophers, but represents a genuine breakdown in the consistency of physical law. A situation in which the equations of physics would have no solution. And while various resolutions have been proposed, including branching timelines and self-consistency requirements, the simplest resolution, and perhaps the most beautiful, is that such situations simply cannot arise, that the structure of space-time itself prohibits the formation of these problematic loops. We might also mention, gently, the cosmic censorship conjecture proposed by Roger Penrose, which, though it concerns singularities rather than time travel, speaks to the same deep theme, which is that the universe appears to hide its most extreme features behind horizons, wrapping its infinities in event horizons that prevent them from disrupting the orderly behavior of the cosmos. And while this conjecture too remains unproven, and while there exist mathematical solutions that appear to violate it, the universe we observe seems to respect it, clothing its black holes in darkness, keeping its singularities private, maintaining the kind of predictability that allows planets to orbit and chemistry to occur and thoughts to unfold in sequence. And this brings us to what is perhaps the most important realization of all, which is that these boundaries, these apparent limitations, these closed doors and inviolable horizons are not prisons in any meaningful sense, but are rather the very conditions that make experience possible. For, consider what the universe would be like without light cones, without the strict ordering of cause and effect, and you will find that it would be a universe in which nothing could happen, because everything would happen simultaneously, in which no memory could exist because the past would not be protected from the future, in which no meaning could persist because meaning requires sequence, and sequence requires causality, and causality requires the gentle boundaries that we have been discussing. The light cone does not separate you from the universe. It is the structure through which you participate in the universe. It is the architecture of experience itself. And when you understand this, the sense of imprisonment dissolves into something more like gratitude. Like the gratitude you might feel for the walls of a house that do not trap you inside, but rather create the inside in which you can rest. And perhaps that is the right note on which to let these thoughts settle, like sediment drifting to the bottom of a still pond, which is that the physics of isolation is also the physics of coherence, the physics that allows one moment to lead to the next, that allows causes to precede their effects, that allows you to close your eyes now and trust that when you open them, the universe will still make sense. And so we return now to where we began, which is to say, we return to you, here, tonight, in whatever quiet place you have chosen to rest. We have traveled through the mathematics of space-time, through the geometry of light and causality, through the strange and beautiful constraints that govern what can touch what across the vast distances of existence. And now we come back to the most immediate truth of all, which is that you yourself, in this very moment, are the center of your own light cone, a structure that extends outward in all directions, backward into the deep past and forward into the unmapped future, connecting you to more of the universe than you might ever have imagined possible. Your light cone, the one that belongs specifically to you, to this moment, to the particular coordinates of space and time that you currently occupy, contains within its past portion approximately 2 trillion galaxies. This is a number that was revised upward in recent years, as astronomers using the Hubble Space Telescope conducted deep surveys of apparently empty patches of sky and discovered, in those seemingly vacant regions, galaxy after galaxy after galaxy, stretching back toward the earliest epochs of cosmic history. 2 trillion is a difficult number to hold in the mind, and so there is no need to try too hard, but it is worth allowing yourself to appreciate, in a gentle and unhurried way, that all of these galaxies, every one of them, reside within the past light cone that surrounds you at this very instant. Light from each of them has had sufficient time, given the age of the universe and the distances involved, to travel across space and reach the location where you now lie, which means that in principle, if you had sensitive enough instruments and enough patience, you could gather information about each and every one of those 2 trillion island universes. They are all part of your past, all woven into the structure of causality that makes you who and what you are. Let us consider, for a moment, the gentle arithmetic of how your future light cone expands as time passes. In 1 second, starting from now, light travels 299,792 kilometers. This is the fundamental speed limit of the cosmos, the same constant we have discussed throughout our journey together. And it means that 1 second from now, your future light cone will have grown to encompass a sphere of that radius, a sphere containing everything that lies within 299,792 kilometers of where you currently rest. This is a considerable distance, reaching well beyond the Moon, which orbits at an average distance of about 384,000 kilometers from Earth, and so within approximately 1¼ seconds, your future light cone expands to include our nearest celestial neighbor, that pale and pock-marked companion that has watched over sleeping humans for as long as there have been humans to sleep. By morning, let us say 8 hours from now, the expansion becomes more substantial still. In 8 hours, light travels approximately 8.6 billion kilometers, and so your future light cone, by the time you wake, will have grown to encompass everything within that radius. This is a distance that carries you well past Jupiter, which orbits at roughly 778 million kilometers from the Sun, and past Sat, which circles at about 1.4 billion kilometers, and past Uranus at approximately 2.9 billion kilometers, and past Neptune at 4.5 billion kilometers, and past the dwarf planet Pluto, which at its average distance is roughly 6 billion kilometers from the Sun. By morning, your future light cone will have reached into the cold, outer regions of our solar system, into the realm of scattered disk objects and the inner edge of the Kuiper belt, encompassing a vast spherical volume of space that, although empty of stars, is nonetheless part of your possible future, part of the cosmic territory to which you are causally connected. Voyager 1, the spacecraft launched by NASA on September 5, 1977, is currently approximately 24 billion kilometers from Earth, and so it lies well beyond the radius your future light cone will reach by morning. If you wished to send a message to Voyager 1, a radio signal traveling at the speed of light, that message would take approximately 22 hours to arrive. This means that any thought you might have right now, Any intention you might form, any signal you might wish to transmit, could not possibly reach Voyager 1 until nearly a full day has passed. The spacecraft is that distant, that far removed from the center of your light cone, and yet it remains within your future light cone if you are willing to wait, as the geometry of space-time assures you it must be. It was from Voyager 1's position, back on February the 14th, 1990, when the spacecraft was approximately 6 billion kilometers from Earth, that the famous pale blue dot photograph was taken. Carl Sagan, the astronomer and science communicator who had advocated for the photograph to be captured, later reflected on what that image revealed about our place in the cosmos. The Earth, in that photograph, appeared as a tiny point of light, a fraction of a pixel in size, suspended in a scattered ray of sunlight. And Sagan observed that everyone you have ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. He noted that the aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on that single pixel visible from Voyager's distant vantage point. This reflection, gentle as it is, reminds us that light cones are not merely abstract mathematical structures, but the very medium through which all human experience is woven into the larger fabric of cosmic time. Within your past light cone tonight, there are events stretching back to the very earliest moments of the universe. The first stars, population threes, stars as astronomers sometimes call them, ignited approximately 200 million years after the Big Bang, when the universe was still young and largely dark, filled with cooling hydrogen and helium that had not yet been processed through stellar fusion. Those first stars were massive and short-lived, burning through their nuclear fuel in mere millions of years and then exploding as supernovae, seeding the cosmos with heavier elements that would eventually coalesce into later generations of stars, into planets, into the carbon and oxygen and iron that make up your body. The light from those first stellar ignitions, although long since stretched into the microwave and infrared by the expansion of space, is part of the cosmic background that fills your past light cone, part of the ancient radiation that permeates all of space and can be detected with sensitive instruments. The formation of Earth itself, approximately 4.5 billion years ago, is also contained within your past light cone, which perhaps seems obvious since you are resting upon that very planet. But it is worth noting that the causal chain linking you to the protoplanetary disk from which Earth accreted is an unbroken thread running through space-time, a continuous path of cause and effect that connects the gravitational collapse of a cloud of gas and dust to the particular arrangement of atoms that constitutes your body at this moment. Every ancestor who ever looked up at the night sky, wondering about the stars, is part of your past light cone as well. Every one of them, from the earliest hominids gazing at the band of the Milky Way with no understanding of what it was, to the ancient astronomers who named the constellations and tracked the movements of the planets, to the scientists who eventually worked out the geometry of light cones and the structure of space-time. All of them existed along world lines that intersect with yours. All of them contributed in some way to the circumstances that led to you being here. Now, J.A., listening to these words in the quiet of the evening. There is a phenomenon that astronauts have described, particularly those who have traveled far enough from Earth to see the entire planet as a single object against the blackness of space. Frank White, a space theorist and writer, coined the term the overview effect in 1987 to describe this experience. Astronauts who have witnessed Earth from orbit or from the lunar surface often report a profound shift in perspective, a sudden and visceral understanding of the fragility and unity of our planet, a sense of being fundamentally connected to all life on Earth and to the cosmos beyond. This experience, although it occurs at the level of human psychology and emotion, can be understood in terms of light cones as well. For what the astronauts are perceiving is the visual evidence of their causal connection to an entire world. The direct experience of light traveling from every illuminated portion of Earth's surface into the past light cones of their observing eyes. The overview effect is, in a sense, the emotional recognition of what the mathematics of space-time has been telling us all along, which is that we are not isolated beings floating alone in an indifferent void, but participants in a vast web of causal relationships that spans the observable universe. You are not trapped within your light cone. It would be easy, perhaps, to think of the constraints we have discussed as a kind of imprisonment, as walls that confine you to a small region of an incomprehensibly vast cosmos. But this framing misses something essential about the nature of light cones and the causal structure of space-time. You are woven into a structure that connects you to the observable universe in its entirety. Every photon that reaches your eyes tonight, every particle of light that enters your pupils and triggers a cascade of electrochemical signals in your visual cortex, was permitted by the geometry of space-time to make that journey. The light from the stars overhead, the glow of the moon, if it is visible, the faint smudge of the Andromeda galaxy, if you were to look toward the constellation of Andromeda on a clear, dark night. All of these are yours by cosmic right, part of your past light cone, connected to you through the universal medium of causality. The Andromeda galaxy, also known as Messier 31, is approaching the Milky Way at a velocity of approximately 110 kilometers per second. This motion, driven by the mutual gravitational attraction between our galaxy and theirs, will continue for billions of years, bringing Andromeda ever closer until, in approximately 4.5 billion years, the two galaxies will begin to merge. The collision will be a slow and stately affair, unfolding over hundreds of millions of years. As the spiral arms of both galaxies are disrupted and reformed, as stars are flung into new orbits, as gas clouds compress and ignite into bursts of new star formation. The Andromeda galaxy is within your future light cone. Its destiny is intertwined with the destiny of the Milky Way, and therefore with the long-term future of everything that exists within our galaxy, including the descendants of life on Earth, if any survive that far into the future. Rest now within your cone of light. The structure that surrounds you, extending backward 13.8 billion years to the Big Bang and forward indefinitely into the unmapped future, is not a prison but a home. It is the portion of space-time to which you are genuinely connected, the region of the cosmos that is truly yours in the deepest physical sense. Beyond your light cone, there may be wonders beyond imagining, galaxies and stars, and perhaps even other forms of life, but those regions are as unreachable as they are unknowable, separated from you by the fundamental geometry of existence. Within your light cone, however, lies more than enough. 2 trillion galaxies, the entire history of the cosmos since the first light emerged from the primordial plasma, the full sweep of life on Earth from the first replicating molecules to this very moment, and a future that extends outward at the speed of light, encompassing more with each passing second. Your breath rises and falls. Your body rests upon a planet that formed from the ashes of ancient stars. Above you, if the sky is clear, light is arriving from sources both near and unimaginably distant. Each photon a messenger from somewhere within your past light cone, each one permitted by the laws of physics to complete its journey to your eyes. You are held within this structure as gently as you are held by the gravity of Earth, and there is nowhere you need to go, nothing you need to do, no escape you need to plan, for you are already exactly where the geometry of the cosmos has placed you, at the apex of your own light cone, connected to everything that has ever been able to touch you, and open to everything that ever will.